All right, I'm recording. Okay, record it. I made a wrong statement yesterday. I just realized this morning. Okay, the wrong statement I said is f of x, right? This function, and its inverse is f of -1. It's the same as the function itself. Okay, so that's no problem. But what I said, this is the only one with such feature, and that is wrong. Okay, this is not the only one. This is not the only one. The other one would be, so this is not the only one. So the statement I made, I said this is the only function whose inverse is the same as the function itself. That is a mistake. Okay, so wrong to say this is the only function whose inverse is the same as the function itself. Okay, I apologize for that. I certainly should have thought a little bit more. Okay, so make that statement. So this is wrong. Okay, so it's wrong to say that. So please write it down. Okay, if you listen to the recordings in the past recordings, I said this and I knew it was on recording. There's no way to escape that evidence, right? But I'm correcting myself because the other one, there might be more. Okay, so that's a wrong statement. Okay, the other function that's that also has this problem, has the same, the inverse and itself is the same, is f of x equals to x. Okay, that y equals to x function, right? It was so obvious, it's staring at me, and I made a wrong statement. Okay, so you should have a good laugh. At the same time, you know, we need to be very careful, very, very careful in math to say something, to make some statement. Okay, every statement is made very carefully, and you have to think about it over and over again. Anyway, without further ado, that's my correction. Okay, now continue from yesterday's topics, right? We had discussed about these functions, and at this point, I'd like to review. Okay. Did you guys write down these properties on a flashcard? Because we're going to use them. We're going to use them. Okay. We're going to use them a lot in the future. Okay. Not to mention you're going to use it in calculus class. Okay. Next. Okay. I'd like to review about the composition of function. Okay. Composition of function. If we think about all these functions, function number 1, 2, 3, 4, 5, 6, 7, 8, and then we did number 9, and we did number 11, we did number 13, didn't we? Right? All these 8 functions, I would say how many? 13, 14, right? We have done all of these functions. If we look at basic 1, right? If you look at basic 1, we've done function from number 1 through number 8, right? And then number 9, number 11, and number 13. We've done these functions, right? And these 3 functions are the exponential functions, and these are the, you know, the other commonly used functions. Imagine. Okay, imagine this. Okay, you pick any 2 functions arbitrarily, f function, g function. Okay, and we do the following operation. Okay, the operations we're going to do are f plus g we will get another function. If we do f minus g, we will get another function. If we do f multiply g, we get another function. What if we divide f function by g function, provided that the denominator is not 0, right? We'll get another function. Okay, g of x should not be 0. Okay, so we operate on these functions and we will create a lot more functions. For example, okay, okay, if you look at these first 8 functions, right? We have an x function, didn't we? Yeah? And we have a constant function, didn't we? What if I add them and multiply by m? What would that be? If I give C a different name, mx plus b. Does that look familiar? Right? What else? In the first 8 functions, we also have x squared as a function, right? And we also have x as another function, right? F of x equals to x. And we also, of course, have the constant function, right? What if I make a new function by doing ax plus bx plus c, and I'm going to use the lowercase c? Have I just created another function from the basic function? You guys see that, how the new functions can be built from the basic functions? Yes? Do you guys see that, right? Can you imagine you just keep doing this? You keep just building them by these adding, subtracting, multiplying, dividing. And you're going to create lots of functions. As a matter of fact, lots of polynomials we learned in our algebra class, they can be seen as a creation by adding, subtracting, multiplying, dividing from these basic functions. What is more, there's another operation. Okay, the other operation we call the composite function. Okay, or composition of functions. So this time we're not composing music, we're composing new functions. Okay, Farouz, yes.
Professor, to summarize so far, is that safe to say by adding the 3 different functions? So ax squared is a parabola function, what do we call it? Exponent function, plus linear function bx plus constant function. Add them together, we create a quadratic function.
Correct. We can see it that way. Yeah, we can see it that way because we have x squared. That's the basic unit of a quadratic, right? You multiply a constant, make sure it's not 0. And multiply a constant with x, you have another function, you add them up, you basically create a new rule, okay? So once again, look at the definition of function, right? Each function is a rule. But when you combine these rules in adding, subtracting, multiplying, dividing, we are creating new rules. Okay, let's see, did I record it? Yeah, I did. Okay. So this is what make you see that you can create as many functions as you wish. And all of these functions, they are all special cases under the definition of function. So what you see is that one sentence definition of function is so powerful because it covers so many, as many as you wish, functions. And that's what you enter calculus class. You're going to be dealing with all of those functions and much more. Okay, in this semester, you're going to see all kinds of functions created. In calculus class, you're going to see even more. So let's look at the other way of composing functions. For adding, subtracting, a multiplication, division, I'm not going to elaborate because you have plenty of examples in algebra classes, and it just, for example, right? Just let me give you a quick example on this one, right? If you compose functions, right, you can say, hey, I have a function x, and then I can do ax squared plus bx plus c. I'm going to multiply these two. Will I make a new function? Absolutely. You're gonna make a new function. That's a multiplication. You can do division, right? So we're not going to spend too much time here because this is, once you see this, it will connect to what you have learned before, whether you remember or not. You're going to see more of these in the future. The other way of creating new function is composite function. So we're going to spend a little more time here. Okay, composite function. So that's going to relate to what we talked about yesterday. Let me see. How many of you have seen this symbol, F composite G? Anybody? Yeah. Some of you have seen it, some of you have not. That's okay. All right, so let me show you what it is. Yesterday, I was showing you those machines, right? Showing those, input, output, that sort of thing. This function basically meaning, right? You have an input, and this input will first be taken as input by G. Okay, taken as input by G. Okay, and it produces an output, G of X. Okay, this G of X will be in the domain of F. Okay, so this X is in the domain of G. Okay, this X is going to be in the domain of G. Okay, domain of G, domain of G. Okay, so X is from the domain of G, sorry, G. And taking that input, it produces an output. And this output is supposedly it's in the domain of F. And then this guy can serve as an input for F. Do you guys follow me? So the rule of F would apply to this input and will produces an output. And this output will be F of G of X. It's like a chain reaction. And you're going to see this kind of making of functions being used in calculus class when when you learn chain rule, implicit functions and differentiation of implicit functions a lot. It's just, that's part you have to understand. Okay. And the shorthand notation, the mathematical shorthand notation for this procedure is what? Okay, so let me show you so you have some ideas about how this works, right? Now, we have an input. G applied to this input, so I put it in parentheses. And G apply the rule of G to X. And the output is G of X. Okay, you can see in this little notation, X is the input, G of X is the output. And this output will serve as the input for F. So I put it in parentheses, I'm going to apply the rule of F, and I will produce the output, which is F of G of X. Don't you see that the notation is so neat and clear? Do you guys follow me? Yeah? Input, output, and use it as input for the next function, output. So this notation represents this entire process. Okay, so let me give you some examples. Okay, some of you might have forgotten. Okay, let's practice. Let's practice. Suppose I have a function f of x. Okay, it has a rule, and this rule I'm going to make it the absolute value of x. Right? My g function has a different rule. My g function has a different. My g function is x squared plus 1. Okay, and this process is f composite g of x. That's what it is, right? Okay, right here. I'm just going to put it over here. Okay, and examples. This is our example. How does it work? How does it work? Okay, each function is a rule. This function is a rule, and the other function is a rule. When we compose them, there are two ways we can compose them. F composite G. Okay, so we're going to have f of g of x. That's what it means. And then we always start from the inside and going out. So it's always inside out, inside out. So now you have f. So from inside, g of x is x squared plus 1. So x squared plus 1. Right? We have f of x here. F of x is over here. When x, you see this x as a placeholder. Okay, this x is a placeholder. I can easily take this as a heart. So this will become a heart. You follow me? It's just a placeholder. You can call it anything you wish. When at the placeholder, it's replaced by x squared, what do? You replace that symbol by the same thing everywhere. You follow me? So in the end of this operation, we call composite function, is that we're going to have the absolute value of x squared plus 1. Okay, so let's look at G composite F. Any questions, please? Remember yesterday I talked about the importance of you ask questions whenever you have one? Okay, so please do. So that's G of f of x. Okay, and that equals to, so G of f of x. So we start from inside. So G of f of x. F of x is absolute value of x. Okay, and then we're going to apply the rule for G. The rule for G is such. This is the rule for G. Right? Now, the placeholder is replaced by absolute value of x. So we're going to replace the placeholder by absolute value of x. And then the final answer will be what? What will be the final answer? The final answer will be that guy. We can simplify further, but right now, just, do you guys see everything so far? Any questions? So this is a composite function. So what you see here, actually, after the composition is done in different order. Different order could make a big difference. For example, this guy and that guy, They may or may not be the same. They may or may not be the same. Okay, so would you guys like to try one to composite? No? Okay, I'm gonna give you an example, okay? I'm gonna give you an example, another example. Your turn. Your turn. I'm gonna give you f of x equals to 3x minus 2. Okay, g of x is equals to let's see, x squared plus 5. I would like you guys to do f composite g and the g composite f. F composite f and g composite g. You ready? We can have a breakout session if you want, so you can work with Farouz. Anybody want to work with Farouz? Composite. Compose your function. Anybody want to go to a breakout session?
Professor,
Yes.
I had a question regarding g of x. G of x, we know it is not a one-to-one function. Is that correct?
No, they don't have to be one-to-one.
With respect to each other, they don't have to be one-to-one.
They don't have to be one-to-one. You can composite them. They don't have to be
Yeah.
one-to-one.
So I was thinking maybe if you are going to ask us, are they inverse of each other? No,
Not yet.
because
Not yet. Yeah, we'll get to the inverse because you can compose function any way you want. They don't have to be one-to-one at all.
okay.
Yeah,
Very
but
good.
but then the reason I do this is because yesterday we did what we did there. What we did here.
Yes.
Okay. Under the circumstances, if they are one-to-one, we have these beautiful properties. If they're not, if f is not a one-to-one, no, and these will not be guaranteed. And we're gradually approaching. We just want to get familiar because this guy, okay, because this guy is the f composite f. Okay, so f inverse. Oops. F inverse, why did I put that outside? Okay, so this guy is like this. Do you guys see that? I was just trying to illustrate this symbol. And this one is f composite f inverse. Okay. So I'm just trying to explain this symbol. Do you have any questions?
Thanks, Professor.
It might be a difficult topic for many of you, but just try to see whether you understand it. If you don't understand it, so please let me know. You know, every semester I try something new. This is one of those things I'm trying now. Okay. And we're going to see this many more times in this setting. In this setting. All right, so right now, please try to compose. So far, so good?
Yeah, I copied those in my board, so I'm ready for breakout room if you
Anybody
wanna.
want to go to breakout sessions? I'm going to breakout rooms. Let participant choose room created. Okay, so you go there at your free will. Free will. Composite functions. And of course, you're going to have some homework today. Didn't assign homework yesterday. And then a quiz is coming your way. This is something that if you have taken college algebra, it might be taught in college algebra. But some of these, but this could also be taught as early as in intermediate algebra. But in college algebra, you definitely have had it. But if you haven't had a college algebra, those courses, then this will be a gap that we need to fill. Okay. Composite functions. We can composite any two functions or three functions. We can actually do 3, 4, 5, 6, as many functions as you want to composite them. But we just use 2 as an example, which is most frequently used. In your calculus class, you're going to see a lot of functions that are being composited, compositional functions, and you're going to have to find derivatives of them and chain rules and that stuff. And so you have to know how to handle these functions and how they're making. Let me see. If you stay in this room, I'm going to go ahead with an example. So I'm going to do f of g of x. And this is going to be f of g of x is x squared plus 5. And f of x plus 5. So I'm going to take that. I will get 3 times x squared plus 5 minus 2. If I simplify, I'll have 3x squared plus 13. Did everybody get it? Right, that's how you composite. And order matters. Order matters. Okay, so G composite F will be G composite f of x. And then, oops, typo. Okay, so you're going to have a G of f of x is 3x minus 2. And then you apply the G function. G function is x squared plus 5. So now the x is going to be replaced by that, right? X squared plus 5. Okay. F composite F. So f of x. This is going to be f of, what is f of x? 3x plus 2. Okay, and then what? F of 3x plus 2, we're going to use that rule which is 3x plus 2, and this x will be replaced by 3x minus 2. Right, you can see all these different ways of composition. You can see all these different ways of composition. So let me close all the rooms.
Professor Wang,
Yes.
so for g of fx, you don't have to factor it any further.
No, well, you don't have to. Yeah, you
Okay.
could, but we're not going there. Okay,
Okay,
I think you
so
guys can handle it.
it's okay to leave it as 3x minus 2.
Yeah. Because our main thing to do here is to see the composition, the consequence of composition.
Okay.
All these functions you see at the end of composition, they're not the same. They're not the same. So F composite G is not the same as a G composite F. The order makes a difference. The order makes a difference. Okay. So they're coming back. Okay, so we're going to compare notes. Okay, we're going to compare notes. All right. Thank you, Farouz. How are they doing?
You're welcome. Very well. Just takes time to catch up and think about the concept composition of fraction. What is the step one? Convert it to, parentheses. And then from there, substitute the values and get the final answer.
Yep. So any questions on these? Should I do this over? You see, g of x substitute by g of x, that's straightforward. The question is, how do you do f of x squared plus 5? So when you look at f of x, this is f of x, right? This is f of x, right? This is f of x, right? This is f of x. But what if you replace the input at x by x squared plus 5? You replace that by x squared plus 5. Then you replace this x by 5 also. That's what happened. You guys see that? So it's just substitution. One is substitution, and the other one is you view the variable in the parentheses as a placeholder. A placeholder. Okay, for example, you see x is everywhere, right? In the math textbook, x is everywhere. Why do they keep using x? Why couldn't they use a different name? Well, it's not necessary if you consider x as a placeholder, right? In other cases, you say, hey, I'm tired of using x. I'm going to use a new symbol. Go for it. But no matter what symbol you use, under the circumstances, that symbol is still a placeholder. All right, so do you guys have any questions? Shall we move on? So let's finish the G, okay? So G of x is going to equals to, right? You start from the inside first. G of x is x squared plus 5, right? We know G. This is G, right? We know G of x. We know G of x. If G of x is x squared plus 5, what is G of x squared plus 5? Well, all you do is replacing the input. You see, they're at the same place, right? They're matching. Then replace this x by x squared plus 5 as well. There you go. We have created a new function. So the creation, is everybody back? Okay, I assume so. Okay, you can see this way we can, how many functions can we create by adding, subtracting, multiplying, dividing, now adding the new operation composite? a lot, as many functions as you wish. Those are the functions, a lot of those functions are going to be in your calculus textbook. Okay, and all of these is under the same umbrella we call function. Now you look at the definition of function, how powerful it is. How powerful it is. Okay, let's see. Okay, you guys worry about simplify. Don't worry about it. Okay, don't worry about simplifying. Okay, don't worry about it. You can simplify if you want to after class. Okay, that's not the point. Now, so for any two functions, we can composite, right? But how about these two? What we did yesterday, and we actually were doing compositing functions. We were doing composition of functions that are inverse to each other. Okay, so for function which is 1-to-1, we have some additional benefit. We have some additional benefit. Okay, so we're going to elaborate on these as we move on, right? As we move on. Now we know that every 1-to-1 function has an inverse, right? We still remember the function we studied some time ago, which is, let me bring these functions to our attention, okay? These functions, the exponential functions, right? We worked so hard to graph them, didn't we? Okay. I'm going to bring these questions on the top. Each one of these functions are what? An increasing function, right? And every increasing function is a 1-to-1 function. Okay, listen to the logic. Okay, increasing function is a 1-to-1 function. Is 1-to-1. And a 1-to-1 function has a unique inverse. So every one of these functions, 1, 2, 3, 4, and more of exponential functions, each one of them will have an inverse, right? Do you guys hear me? You guys see do you guys hear the logical argument, right? Every 1-to-1 function has a unique inverse. Because every increasing function is also 1-to-1 function, therefore, every increasing function will have what? A unique inverse, right? For example, f of x equals to 2 to the power x. Take this example, right? We've done so much work for these functions. This function is 1-to-1, and therefore, it has a unique inverse. And how do we find the inverse? We did that yesterday, right? For a specific example. How do we find the inverse? How do we find inverse for f of x equals 2 to the power x? 2 steps, right? Step 1. What do we do on step 1? Come on, guys. What do we do for step 1?
Swap the x and the y.
Swap x, y. Perfect. So x equals to 2 to the power of y. And what's for step 2?
Do we solve for y?
That's right, solve for y. If we solve for y, what do we get? We will get a new function for sure, right? We're gonna get we're gonna get a new unique function for sure. And what is it? If you solve that for y, what do we get? A new function. A new function. Yeah? Does that look familiar to you? Have you seen that before?
Yes.
All right. So now we get to the door of logarithm. Right? Don't worry. We're going to do all we need to do to refresh or learn. Okay? So we have one function like this. It's inverse. It's inverse. F inverse. Oops, x equals to log base 2 of x. These two functions are inverse to each other. What does that imply? The swap implies that their domain and range are going to be swapped, right? And we're going to observe these and look at some other interesting features. We have worked so hard to graph 2 to the power x, didn't we? Yeah. And we will get to graph this guy as well. But before we get to this guy, we better understand what this means, don't we? Do we understand it? Okay, so let me introduce the definition of logarithm. Okay, let me introduce the definition of logarithm, which is, you know, it's already here. It's already here. Okay, it's already here. But I want to just introduce the definition. It's a general definition of logarithm. Okay, so if you have a logarithm base of any base, right? When we were talking about exponential function, we said that the base of exponential function has to satisfy certain condition. Okay, and what was that condition, guys? Do you still remember? Do you still remember? Right?
Did you ask me, Professor?
I'm asking everybody.
Everyone, okay.
Yeah. Okay. Recall. Okay, when we were talking about 2 to the power x, e to the power x, right? 10 to the power x. We even talked about 3 to the power x, didn't we? And so on and so forth. We mentioned there's a family of exponential function. Family of exponential function. And we introduce a symbol, base to the power of x, and that represents the family of exponential functions. So the b can be 2, can be 3, can be e, can be 10, can be 1 over e, can be half. Remember? Yes, we did all of that, didn't we? Now,
That cannot be 1. Yes.
That's right. B cannot be 1. B must be positive. It cannot be 1. And this same condition is going to be imposed over here for logarithm base B. Okay? And that same condition is going to be imposed. All right? It's the same B. Okay? Same requirement for the base. And what is more, logarithm written like this, meaning that b raised to the power of a triangle is equals to baloney. Okay, this symbol actually, it's a Greek letter, isn't it? Is that a Greek letter? It's called sigma. Am I right?
Omega.
Oh yeah, omega. It's not sigma. That's right. Omega. You're right. Omega. A lot of the time in this class, I tend to use it as a baloney. Okay, just to get your attention. Just to get your attention. Okay. Omega. Thank you, Farouz. Omega. So this is the general definition of logarithm. As it applies, suppose I choose base equals to 2. Okay. What happens if I choose base equals to 2? In the case of base equals to 2, what happens? This is going to be 2, and that's going to be 2. Let's see if we know how to operate this. Okay, the goal is to get familiar with logarithm, right? The goal is to get familiar with logarithm. All right, so I'm going to take this guy and then bring it down. Okay, we don't need to write this b equals 2 anymore because it's already there. Now, it looks like that the exponential form and logarithm form are related. They're related, aren't they? You see, they even have the same base. But the omega, it plays a different position, or baloney plays a different position. In this form, it expresses the exponent only. In this form, it expresses the power. So this is the power form. This is the power. This is the exponential form. So this side is called exponential form, and this side is called logarithm form. You guys get it? Exponential form, logarithm form. For example, 2 to the power of 0 equals to what? What does 2 to the power of 0 equal to? Come on, guys, you know it.
1.
1, that's right. And 1 is in the place of omega, so 1 is going to go here. 0 is in the place of triangle, so 0 is going to there. So log base 2 of 1 is equal to 0. If this is the one side of your palm, and this guy is the other side, they're saying the same thing. They're saying the same thing. They're saying that 0 power 2 is equals to 1. And log base 2 of 1 is 0. It's also saying 0 power 2 is 1. Do you guys see that? Yes, that's the definition. And next, I want you guys to practice. I'm going to give you some values. Okay, I'm going to give you power here, and you're going to substitute omega with the right number and triangle with the right number. Did you get it? Did you guys get it? Do you know what to do? Do you know what to do?
Yes.
Okay, good. Go for it. Anybody want a breakout session?
I have some tricks and techniques I can share with the class if they choose to.
You want me to open the breakout session? Breakout rooms. feel free to work with to work with Farouz if you want, or you can stay with me. Okay. So 2 to the power of 1 is 2, right? And that means log base 2 of 2 is equals to 1. 2 to the power of 2 is 4. And that's going to be 4. And that's going to be 2. Okay, I'm leaving you to complete the rest. So logarithm is another way of saying the same thing. And the other way to say the same thing with a different emphasis, it emphasizes the exponent, which raise the power, okay? It's a notation you must get used to. You must know how to use it, because there are lots of points out there in calculus classes waiting for you to gain or to lose. If you're done, I would like you guys to practice with log base 10. Log base 10. Log base 10 it's a default case. If you write log without indicating the base, it will be by default considered base 10. So log omega equals to triangle, okay? Well, this is also called a common log. Common log is called a common log for a reason. Common log, okay? It's used in a lot of other fields that logarithm are used. In the mathematical series, in the calculus series, actually e to the power x is used the most. Okay, but common log is more used in some other applications, in earthquake studies and so on and so forth. Okay, for example, the Richter scales. Anyway, so I'm going to close the rooms. I believe they're about done. Okay, we have 55 seconds, 54 seconds to finish. Any questions, you guys? Am I going too slow? Am I going too slow? No. Okay. Do you have any questions? So please never hesitate to ask a question. Okay, please. You're helping yourself, you're helping your classmates as well, you're helping me as well. All right, so don't hesitate. All right. Now, do we have any trouble doing these? Yeah. For the last one, I didn't quite finish, which is 8, right? And this is 8. And this is going to be what? What number should be replacing the triangle here?
3.
3, excellent. Another phenomenon I want you guys to see is that you can also do this. 2 to the power 0, right? Log base 2 of 2 to the power 0 is 0. This 0 matches that 0 when these two bases agree with each other. Do you see that? 2 to the power 1, put it here, boom. When these two match, the power is going to be the answer. 2 squared, do you guys see that? That's one of the properties, right? If you learned that before, right? Do you guys see that? Do we agree? This is just a different way of saying the same thing, right? Different way of saying the same thing. All right. I'm going to give you another set of exercise, okay, with base 10, base 10. Base 10. Okay, common log. So first, let's talk about the notation. When the base is 10, we can omit the base and write it as just log. And this is called a common log. Common log. So whenever you just write log, followed by whatever quantity, okay, it will be treated as by default, the base is 10. So you can just feel free to use the common log. And this is the log button that's also in the calculator, in the most calculators, okay? Some more expensive advanced calculator, they have both common log and natural log. But most calculators should have common log. Okay, so that's the least expensive calculator will have common log. But anyway, without further ado, I'm going to give you some exercises to practice use common log. Very similar to, right? The first one I'm going to give you is that I'm going to put this number as 0, 1, 2, 3. Now you're going to fill out the rest. You get it? You're going to fill out the rest, okay? Figure out these numbers and put them on the other side. You guys follow me? And get those respective numbers in these places.
Professor, that could be another breakout room activity if
Sure.
you choose to.
Yeah, of course. If you wish. That's a great idea. Thank you, Farouz. Farouz is a great help. All right, if you like to go to the breakout room, go for it. Okay, we're going to practice how to do these log things. We're going to practice a lot of it. Okay, we're going to practice a lot of it. If 10 to the power 0, 10 to the power 0 is, I'm doing the easy one, you do the hard ones. How about that? It's 1, right? So log 1 is equals to 0. Okay, so the power is specifically expressed. You guys are going to do the rest. Okay, I'm going to add a few more for you. How's it going? Any questions? Mm-hmm. So it goes pretty smoothly, huh? Okay, so I'm gonna close. Sorry for those if it's too early. You still have 56 seconds. Five seconds. 5 seconds. How's everybody doing here? Farouz is back. Thank you, Farouz. Great
Thank you,
help.
Professor. Thank you.
Of course. All right. So let's compare the notes, right? I'm gonna do the easy ones. You do the hard ones, right? So log 10. Sometimes you want to know, how do I read it? Okay. So the way I'm reading it is the way you should read it. Okay. So log 10 is 1. Okay. If you like to make it sound more relevant, you can say common log. Common log 10 is 1. Okay. Meaning 1 power 10, 1 power 10, this invisible 10, right? Because by default it's supposed to be 10. 1 power 10 is 10. Now, omega is 100 over here. So common log 100 is what? It's 2, because 2 power 10 is 100. So this is 1000, right? Common log 1000 is 3. Common log a million. Is that a million? Okay. A million. 10 to the power 6 is what? 6. And this is going to be what? This is 10 million, right? Is this 10 million?
Yes.
10 million. So 10 to the power 7. Common log 10 to the power 7 is 7. Okay. So the reason I introduce, we want to do some exercise with the common log here is because it's used very much in the earthquake measurement. Okay. Suppose the power of the earthquake is 10 million. The Richter, oops, what did I do? Oops, sorry. The Richter scale. The Richter scale is 7. If the earthquake of the power is 1 million, that Richter scale is 6. Okay, have you guys experienced an earthquake? I think we all probably have experienced an earthquake, right? Yeah. I experienced the Northridge earthquake. That was about 6 point something, right? So if you look at the Richter scale of earthquake 6 and Richter scale of earth 7, okay, the difference between 6 and 7 is 1. But the actual power of the earthquake is what? It's 10 times stronger for Richter scale 7. You follow me? So the Richter scale is just to basically try to make the numbers smaller, more manageable. But the actual power from Richter scale of 6 to Richter scale of 7, even though from 6 to 7 is only 1, the actual power of the earthquake for 7 is 10 times stronger. It's 10 times more destructive. Does that make sense, you guys?
Professor,
When you
and
reach-
sorry,
Yeah. Go
and
ahead.
if he had the Richter scale 9.9, that would be how many times a stronger destructive force
I
compared to
know,
six?
that's a good question. If the Richter scale is 9.9, oh my God, we probably all die.
I mean, with respect to Richter scale 6, 7 is 10 times stronger force. And
Let's
the
just
nine
use 9. Let's just use 9. Richter scale 9. How much stronger is Richter scale
compared to
9
6,
compared to Richter scale of 7? What do you do? What could we do?
Isn't it 1 billion?
Will be 1 billion. If it's Richter, if it's 9, right? If this is 9, right? And this has to be what? You're absolutely right. It's a billion. But how much is stronger, right? So omega is going to be 10 to the that's a billion. What's the difference between this is 10 to the power 7, right? 10 to the power 7, 10 to the power 9. 10 to the power 9 is 100 times stronger. Even though the number difference is only 2, right? But Richter scale of 9 is 100 times stronger than the Richter scale of 7. Does that make sense to us,
yes.
everybody? So when I heard Farouk said 9.9, my legs is shaking.
That was 1,000 times almost more strong, right?
I know, it's almost 1,000 times stronger than the strongest earthquake I have ever heard of. Isn't that pretty scary? Did Farouk scared us?
We had 9.1, but hopefully we don't have 9.9 ever.
Oh, the strongest is 9.1?
I have heard that, yes, we can Google it and find
Oh
out.
my God. Oh my God. You guys may want to investigate. It's pretty, the earth is pretty, it can be very violent. It can be very violent. But anyway, without further ado, you can see that you know, the use of logarithm oftentimes is just to create index and like such as Richter scale to tell us the magnitude. But from that, we need to understand from 6 to 7, it's just one number increase, but it's 10 times stronger, 10 times stronger, 10 times more destructive. Okay, so that's what it is. All right, so without further ado, we got a new function, didn't we? Didn't we get a new function? It's a new rule, right? And this new rule is created from 2 to the power x. And we got this new rule. So let's observe its domain, range, intercepts, and so on and so forth. Are we ready? This is the new rule. You can see we talk about 2 to the power x is a rule, right? It's a function. For each input, there's a unique output. This new rule, we know that this function exists because because 2 to the power x is a one-to-one function, therefore it has an inverse, and the inverse, of course, is a one-to-one function as well, right? So let's take a look at how the graph will look like for this function. Are we ready? So we're going to practice more on logarithm. Okay, so now we're going to do some more calculation, and this time everybody should roll up your sleeve. If necessary, we're going to open that breakout session. Okay, so I'm going to put log base 2 here. Okay, our input, I'm going to give you the input, and we're going to create a table for input, output, and you know what comes next, right? The next is just we're gonna create a picture. We're gonna create a picture. That picture, creating that picture part is called analytical geometry. Okay, it's called analytical geometry. So now, without further ado, I'm gonna give you some numbers. Okay, one of the numbers I'm gonna give you some easy number first. Okay, 1, 2, 4, 8. That's the input. And you will create the output for me. Okay, and since we like the notation, we know this is the inverse function, so why not? Let's do it. Right, let's just do it. Getting familiar with these notations. So you're gonna figure out the output. Are you guys there? Knowing the definition of logarithm now. So let's figure out the output for log base 2x. So this is going to be 1, 2, 4, 8. So what will be this output? New rule, right? This is a new rule. This is a new rule. New rule, new look. New rule, new look, right? We're going to get a new look of the function because the rule is different. Do we need a breakout session? You want to work with Farouz?
I copied some of this question on the board. If I'm ready, if they choose to.
Yep. So I'm gonna set up the breakout session, breakout rooms, if you want. Okay. Complete voluntary. One, 2, 4, 8. You might have guessed it, right? I picked these numbers because they're easy. They're easy. Okay, I'm gonna give you harder numbers very soon. As a matter of fact, I'm gonna get started on doing that. Delete that column, no need for now. And I'm gonna insert more rows. Okay, so I'm gonna give you I'm gonna give you a quarter. I'm gonna give you just half and quarter, okay? So you're gonna find from the input to find the output. So this is half. And this is gonna be a quarter. You're gonna have to figure out the output. All right, I think it's let's move. Let's come together. Okay, I'm closing the room. Now, for those of you who are in the room, let's fill out the blanks, right? What does this input, what is log base 2 of 1 equals to? Let me see any answers from chat. Perfect. You're right, Marco, right? So that's 0. So when input is 1, output is 0. Now, how about this guy? Log base 2 of 2, what does that equal to? 1. Too easy for you, huh? Too easy for you. Wonderful. I'm glad you got it. Log base 2 of 4. I made a typo here, okay? Accidentally, I delete some number, I delete the base. Log base 2 of 4. Thank you, Farouz.
You're welcome. Thank you, professor. Thank you, class.
2. Excellent, Christopher. So when the input is 4, the output is 2. How about this last one? 3. Wonderful. Wonderful. Okay. How about the new numbers I put in here? One is a half, the other one is a quarter. What would that be? Yes.
-2.
Okay, this is a -2. Christopher already have the whole points out there. That's -1. Perfect, you guys. Amazing. Amazing. Now, this is a quarter, comma, -2, right? Because you can write this as 2 to the power -1, right? You can write this as 2 to the power -2. So in this case, the exponential form is very good, right? It's very, very good, especially when you have the same base. Now I'm going to give you a few more, okay? 1/8. What will be the output for 1/8? Perfect. Perfect, Elijah. Wonderful. So now I'm going to give you 2 more. One is 0 and the other one is -2. Could you tell me what are the output for those input? If you find the input, then we'll be making 2 other points. What would that be? Let's see what's on the comments. Nothing. Okay. In order to figure out the value for log base 2 of 0, we're trying to find a number. We'll be trying to find a number. And this number, which is triangle, 2 to the power of that triangle should equals to 0, right? And for this other one, right, we're going to try to find a number. Okay, and 2 to the power of that number, whatever symbol I use, I just need a numerical value for it, and should equals to -2. Okay, so I'm looking for these two numbers. We search high, we search low. Have you searched high? Have you searched low? Have you found them? Alexa says 0, 1. So when input is 0, the output is 1. Is that what you're saying? Okay. That's not going to work, right? I always like the self-check, right? You figure out yourself. You don't need the answer from the back of the book. You can figure out yourself. Yeah, I plugged in. Can you re-explain? Oh, okay. Yes, for quarter, for the output of quarter, right? 1/4 is, we're trying to figure out what number power 2 equals to quarter. -2 power 2 is going to be equals to a quarter, right? And -1 power 2 is going to be 2 to the power -1. So that's going to be half. And if you look at this, you know, 4 equals to 2 squared, right? So 1/4 is, if you write in the exponent form, so that's going to be 2 to the power -2, right? And this is if this were 1/2, one half is 2 to the power of -1. That is -1 power 2 is 2 to the power -1. Does that make sense? I see. Okay, got it. Good job. Okay, I always welcome questions, so please. So now, obviously, wouldn't -2 be reflected across the y-axis? That's right. -2 is the input. So what will be the output? Go ahead, one, say something if you wish.
No, it's just a thought that I had saying, because from before we also had a negative number and we would just reflected it across the y-axis from.
Well, you have to be able to find the output, right?
Yeah, that's what.
Right? If you
Yeah.
find the output with that input, yes, it's going to be on the other side of y-axis for sure. But the question is, now we need to identify that output, because every point we plot is made of a pair of numbers. You have input, you have exactly one output, right? Did you hear the definition of function? For each input, we have exactly one output. For each input, we have exactly one output. We have to have two numbers to make that plot. Now the question is, do we have any answer for this guy? Can we find the number? Because if we can find the number, that power 2 will give us 0, then that number will be the answer here. Does that make sense? According to definition, right? According to definition. So what is that number? What is that number?
Professor, while we are waiting, can I add something in
Sure.
regards to inverse function as you have it in the column? These are inverse function of x. What about looking at the original function f of x, and then watch for its domain, because if you go with the, f of x, and then output of f of x is going to be input for f inverse of x. Therefore, with the notation you were reminding us, if the input is in the domain of the f.
You can, yes, you can think in that direction, right? Because the domain and range is a swap, right? It is a swap.
Yes, ma'am.
We'll get to that part as well. You can certainly think from that perspective, but the matter of fact is such a number does not exist. Okay, does not exist. You haven't found it, right? Let me assure you, nobody have found it. Nobody has found it. They don't exist. Okay, so if you have an input, right? If you have you given an input and its output does not exist, according to the definition of function, for these two inputs, there's no outputs. Can these numbers make their way to the domain? The answer is no. So the domain of log base 2 of x shall not include 0. It shall not include any negative number. You follow me? Okay, so that's the point I want to make. And we also have another very powerful statement. Okay, we also have a very powerful statement. When we study 2 to the power x, right? Peruse just mentioned domain and range. For the function 2 to the power x, what is the range of 2 to the power x? Do we still remember that one sentence statement about domain and range? Domain range in one sentence for 2 to the power x, what was it? 2 to the power x is positive for what? For any real number. This is that powerful statement. That's what it means for any, because no matter how many times, no matter you use what number, okay, any number you use here, whether it's a triangle, whether it's a bologna where you use it, anything you use there, it's always going to be positive. It will never be 0. So this will never happen, not in a million years. And this will never happen, not in a million years. You guys follow me? Therefore, okay, these numbers are not going to be in the domain. So what numbers should be in the domain? These numbers are not in the domain because for each one of them, there's no output. So it violates the definition of function. Therefore, they don't make their way to the domain. Now we can see the input can be fraction, decimal, whole number, whatever, but the input must be positive. You follow me? Does everybody follow me? Okay. So these will never happen. Let me mark it. Okay. These will never happen. Never happen. Okay. So these cases, because these cases will never happen. Okay. Because these cases will never happen. So we have no solution to them. Undefined. Undefined. So what should be the domain of log base 2 of x? This new rule. It should be x is larger than 0. Okay, we have a couple minutes left, but that's right, greater than 0. Very good comments there. Okay, you got it. Okay, And what is the range? What is the range of log base 2x? Okay, look at this table we have done, right? Look at this table we have done. The input must be positive numbers. What happened to the output? The output can be negative 0 positive. The output can be negative 0 positive. Now let's plot these points. Let's plot these points. Okay, so let's plot these points. Are you guys ready? Are you ready? Okay.
Yes.
Let's plot these points and summarize it. Okay, I'm going to leave the summary for you today. Okay, I want you to try it. And tomorrow, we're going to come together to compare our notes on the summary. This is going to be -4, 5. Okay, so I'm creating this rectangular system. I'm going to plot these points. Okay, we don't have a whole lot of points left. And of course, we're going to continue tomorrow. But let's put these points in place. I put the points in place. Okay. So put these points in place. Okay, I'm just going to put a handful of points. Okay, so quarter input, the output is -2. Red dot. Next one, half input, output -1. Input 1, output 0. Input 2, output 1. One more, or 2. So how about we connect the dots? Log base 2 of x. Dots are connected. That's the curve. That's a curve. Okay. The input, you see, the input will never get to 0. It can get to 0, can be very close to 0. Imagine the number is, the input can be as close to 0 as possible, as close to 0 as possible. In that case, what will happen for the output? Okay, the input may be as close to 0 as possible. What happened to the output? The output may be as low as possible. So how do we describe this process? How do we describe this process? Okay, so I'm going to put a closure for this description, and then we're going to talk. We'll continue this on tomorrow. Continue this tomorrow. Okay. Clear all drawings. This is something very useful to your calculus class. Okay, so I'm going to put this over here. Just bring the picture over here. The description is when x is approaching 0, from larger than 0, we have a little positive sign on the shoulder. Log base 2 of x is approaching -infinity. Okay, that's the mathematical description of when x is approaching 0, as close as possible to 0, the output is going to be as low as possible, infinitely. You guys follow me? Domain, range, intercepts. Today, I want you guys to try to summarize, similar to those we've done for other functions. Okay, just give it a try, okay? Learn this technique of summarizing. Okay, after all, being done. you're gonna be benefited tremendously. You're gonna need that skill in calc. Okay, and of course for today as well. So I will see you guys tomorrow. Okay, there will be homework for you. There will be homework for you. Okay, you're gonna be logarithm and you're gonna have a quiz soon. I didn't give you homework yesterday. Okay. All right, I will see you guys tomorrow. Good job. Good
Professor,
job. Yes.
30-second announcement to the class. They can find me tomorrow and Thursday from 3 to 6 Math Study Center.
Thank you, Farouz.
You're welcome. Thanks.
Thank you, guys.
See you tomorrow.
See you guys tomorrow. Wonderful job. Great participation. Okay. If you have any questions, so please don't hesitate to ask me.